Today we're going to talk about behavior of gases. We're going to talk about how we describe gases, what we expect them to do, and something we call the gas laws. So some general background information about gases, a lot of which you already know, is that gases have very large distances between their particles. Particles are very spread out in relationship to their size. The intermolecular forces, or forces between molecules, are very weak. Gases, they have a lot of kinetic energy. They're a very high energy state of matter. And we expect their particles to move constantly. They don't stop moving. They move very randomly. And although they move randomly, they do take straight line paths. Their paths can be diverted by bumping into things. Gases are also very compressible because of those large spaces between the gas particles. In order to describe a sample of gas, we'll be using pressure, volume, and temperature. We're going to discuss what the amount of gas has to do with this, but in terms of our calculations, we don't actually worry about that too much. Pressure is defined as collisions, gas pressure is defined as collisions between gas molecules in the sides of a container. The units that we're going to use for pressure are going to be kilopascals or atmospheres. If you're thinking about filling up your tires, here in America, we use pounds per square inch, or PSI. Volume is the amount of space an overall sample of a gas takes up. We'll typically talk about this in terms of either milliliters or liters. Temperature is a measure of the average kinetic energy of particles in a sample of a gas. It's an overall picture at how fast particles are moving. Remember, when we talk about average kinetic energy, not all particles have the exact same speed. So this allows us to say, okay, on average, how fast most of them are moving. In this part of this unit, we will talk about our temperatures in Kelvin for a number of reasons, not the least of which is we won't have any negatives. The amount of gas is also important, the number of actual particles there, and that would be in the unit of moles. We don't actually worry about this in the calculations that we do in Regents chemistry, although the amount of gas in a sample will obviously affect things like volume and pressure. So temperature, when we talk about this particular part of this unit, we do have to have our temperatures in Kelvin. Oops, stop the way for a minute. The reason that we need to have our temperatures in Kelvin is because of this right here. Kelvin is an absolute scale. 0 Kelvin equals 0 kinetic energy, no molecular movement. So there's a direct relationship between temperature and the movement particles have. If you're at 0 degrees Celsius, there is still particle movement. Which means you can't say, hey, that's telling me exactly how much movement is there, because it's really not. So also, just from a mathematical standpoint, Celsius has negatives. So the reason that we use Kelvin is we're not going to get any negatives because this is an absolute scale where there's a direct relationship between kinetic energy and temperature. One table you're going to need to use in this unit is table A. And one thing you'll be using this for is finding the conditions of standard temperature and pressure. Standard temperature can be given as 273 K or 0 degrees Celsius. We'll be using this one. Standard pressure can either be 101.3 kPa, which is the SI unit, or 1 atmosphere. We do calculations using both units of pressure. So kilopascals or atmospheres, the one that we choose will sort of depend on the problem that we are given. So our 3 major gas laws that we cover, we'll actually put them together in one gas law at the end. That'll make our calculations a little bit simpler. The first one is by a guy named Robert Boyle. He actually worked for Robert Hooke. So this guy Hooke, he was the guy who came up with the term cell. So if you remember learning about somebody looking at onion cells and then looking like jail cells, that was Robert Hooke. So you'll actually talk about him when you talk about springs in physics. Hooke actually used to work for a guy named Robert Boyle, and together they studied gas behavior. So what they found, and this is some super real data, if they compared the volume of a sample of a gas to the pressure that that sample of gas is under. So this is pressure over here. That as you increase volume, pressure decreases. So if we think about this, and this is again, you have to hold the amount of gas constant here, and you have to hold the temperature of the gas sample constant here. So if we have a large volume, the particles won't collide with container as frequently. This is considered to be low pressure. This is like being in a large room. If you take a certain number of people and then you take them to a small room where you have a small volume and those people are walking around in that small room, a small volume, you're going to have more particle collisions, it's more crowded, and therefore you're going to have higher pressure. So a nifty little way of looking at this, if you look at these gas particles right in here, where they look more crowded when you're at that smaller volume is when you're seeing higher pressure. As that volume shrinks, that pressure goes up. Next law that we talk about is Charles' law. And a lot of what Jacques Charles and one of his buddies discovered had to do with experiments involving hot air balloons. So hot air balloons were kind of all the rage then. People were doing a lot of experiments with gas laws to determine how to get hot air balloons to fly and how to get them to fly better. If you increase the temperature on a sample of gas but keep pressure the same, the volume will increase. A great place to see this is if you leave a water bottle in your car. So go ahead, open a water bottle, take a few sips out of it, leave it in your car overnight. After that water bottle's gotten cold, so if you take the sips at room temperature and you leave it in a nice cold car, you're going to notice that that water bottle looks shrunken. The opposite thing happens in the summer, and the water bottle will look expanded. The sample of gas inside of it is responding to the temperatures. So what we actually see here is if we have the water bottle in a cold car, that as particles experience a decrease in temperature, they're going to slow down. And as they slow down, they're going to get closer together. And we would expect the opposite thing to happen. As particles speed up, they're going to spread out as much as they possibly can in that sample. So this diagram shows you heat up a sample of gas. Those particles, they actually, if you have a flexible container, what's actually happening is when the particles move faster, these particles as they move faster right here are pushing this container up. So by having more kinetic energy, they're able to push on the sides of the container with more force, thus increasing the size of the container itself. What's kind of interesting about his data, if you look at this volume versus temperature graph, so we got all these little green points right here. So these are some data points that maybe Jacques Charles had. What he actually discovered was that if you extrapolate the data, or you do like the line of best fit, and you extend this down to zero volume, you can actually figure out where absolute zero is. So a lot of kids say, hey, absolute zero, you say it's theoretical, like how do we know where it's supposed to be? We actually do know that pretty well, because we're able to take, oops, I thought I had a good graphic for that, I guess I don't. We were able to take a whole bunch of different gas samples. We take a whole bunch of different volume and pressure, or volume and temperature measurements, and extrapolate them down, and that tends to happen, these temperatures are in Kelvin, but that happens at about -273 Celsius. So that told us where we do expect to find absolute zero. So as the temperature in a sample of gas is increased at constant volume, pressure increases. This is a great example of this is the old aerosol can on fire. Everybody loves to talk about that. Don't try that at home, but you may have been lucky enough to see that. Particles speed up, collide with sides of the container. If those sides of the container are fixed and rigid, those collisions are going to get more forceful, and those more frequent and more forceful collisions give you your increase in pressure. So you do need to know the general mathematical relationships here. So as temperature goes up, that causes volume to increase. When volume is higher, pressure is lower. This is one kind of has a curved look to it. And as temperature increases, pressure increases. And there's a mathematical law for each of those. So if you have an initial volume and initial temperature, it'll relate to a second volume and a second temperature for that same fixed sample of gas. In our first diagram up here, we are actually holding pressure constant. Our value of pressure law, we're holding temperature constant. So Boyle's law is actually stated as an initial volume and initial pressure times each other will equal a second times each other. So you'll notice the upstairs-downstairs relationship in the first one makes that straight upward line. Volume and pressure are next to each other, so that's why you get that relationship where one going up causes the other one to go down. And when pressure and temperature are changed, but volume is constant, we then see the relationship that P1 over T1 equals P2 over T2. What's important to note in all of these is these are fixed samples of gases in terms of the amount of particles in them. So we're not actually changing the amount of gas that are in each one of these. So next we're actually going to combine these into something called the combined gas law, which will make your calculation life a whole lot easier.